Every day I wake up, pour myself a cup of that rich Folgers aroma. The best part of waking up, it's the do-wop in all I do. The mountain aroma, always coming through. Oh, the best part of waking up is Folgers in your cup.
Caffeine is a soft white crystal or powder with an intensely bitter taste when it's in its pure form. It is odorless as there's no gas molecules being given off because it's in a solid state. Caffeine has a molar mass of 194. It is a molecular solid with low conductivity, and caffeine is soluble in water because hydrogen can bond to 6 different places. The hydrogen molecules are highly attracted to the highly electronegative nitrogen and oxygen atoms. So where came the word caffeine? Well, the word caffeine actually originates from the German word of café and the French word of café, which both translate to coffee. But us chemists can call it 1,3,7 trimethyl X-thiamine. Close enough. We can examine the sigma and pi bonds of the caffeine molecule. There are 4 pi bonds, and they are found in the regions of the double bonds. These are our pi bonds. And the remaining bonds are sigma bonds or single bonds. So all of these inner bonds can be considered as sigma bonds. Using VSEPR, we can break apart the caffeine molecule to label the different shapes on the molecule. So the shape of the nitrogen that is bonded to the 3 carbon atoms is trigonal pyramidal. Because the nitrogen has a lone pair. So this lone pair gives it a slightly stronger repulsion between the lone pair of electrons and the bonding pairs of the carbons. So therefore the 3 single bonds are pushed closer together, and this creates an angle of 107.5 degrees. The shape between each carbon atom double bonded to an oxygen and either 2 nitrogens or a nitrogen and a carbon is trigonoplanar. This is considered a double bond according to VSEPR theory. So the shape of the nitrogen bonded to the 2 carbons here is V-shaped with an angle of 104.5 degrees because the nitrogen also has a lone pair there. And because of that lone pair of electron, once again, the single bonds are pushed together, making this a linear structure and turning it into a V-shaped. Once again, we have the tetrahedrals where the CH3s are found on the ends. The intermolecular forces that are present in the caffeine molecule are also known as van der Waals forces. They consist of hydrogen bonding, London dispersion forces, and dipole-dipole forces. Due to the electronegativity difference between the carbon and oxygen covalent bonds and the carbon-nitrogen covalent bonds, the atom with the higher electronegativity, which the arrows are pointing to the one with the higher electronegativity, they will cause an unequal sharing of electrons. This results in the carbon having a partial positive charge. So the geometry of the caffeine molecule allows it to be polar because the negative and the positive ends don't cancel each other out. So that would mean that this is a polar molecule. There are 2 functional groups found in the caffeine molecule, which are amines and amides. In caffeine, there's 1 tertiary amine group, which is found right here. because the nitrogen is bonded to 3 alkyl groups and no hydrogen atoms. The second functional group that is found in caffeine is the amides, which consists of a carboxyl group directly attached to the nitrogen atom. So these groups are located in 2 different places, here and here. So altogether we have amine groups, we have amide groups, we also have methyl, we have an ethene group, and the carboxyl groups, which are my C and my O's. When you ingest caffeine, let's say in your favorite cup of coffee or tea or pop, it is a stimulant of the central nervous system. So as caffeine enters your body, it's going to metabolize into 3 different molecules, which are parexinine, theobromine, and theophylline, which are responsible for increased flow of oxygen, increased athletic performance, increased heart rate, and increased ability to focus. So they break up through 84% paraxine and 12% theobromine and 4% theophylline. So the real question is, this is essentially how caffeine keeps you awake. So adenosine is primarily responsible for making you feel tired. As adenosine builds up in your brain, you begin to feel more and more tired. So caffeine blocks the effect of adenosine in the brain and other body parts. Therefore, adenosine neurotransmitters cannot bind to nerve cell receptors, causing you to feel tired. So since caffeine and adenosine are similar in structure, caffeine can easily bond where adenosine would bond by blocking the effects of adenosine and replacing it with the effects of caffeine. So adenosine slows down the rate of nerve activity, so that's what makes you feel tired. So when you inhibit this, caffeine increases brain activity, and the increase of spontaneous nerve firing and the release of neurotransmitters to stimulate nerve cells through the hormone epinephrine. For my 3D molecule of caffeine, I decided to use these styrofoam balls. I painted them, and then I used toothpicks to denote any double bonds that were eminent, and the yellows are the hydrogens, the blacks are the carbons, and the blues are the nitrogens, and the red is my double bonded oxygen, creating a carboxyl group here. We have a methyl group here, and then we have an amide group, an amine group, and my carbons.